Okay, let's look at some further uses of electromagnetic induction. Have you ever wondered how a microphone works? Okay, well, when you speak into a microphone or you sing, the sound waves passing from your vocal box, okay, into the top layer of the microphone, okay, which inside there is a diaphragm, okay, and this layer literally moves in and out depending on the sound waves, the vibrations of the air particles are right in front of it, okay, and that's going to cause this coil to move in and out, okay, of this magnetic field, north to south, remember, and as it moves in and out, they are 90 degrees to the magnetic field lines. They're going to cut the magnetic field lines, and we're going to get current being induced one way when the diaphragm moves inwards, and then it's going to move in the opposite direction when the diaphragm moves the other direction. Okay, so that's how a microphone works. Okay, how does a speaker work? Well, it does literally the opposite to a microphone, okay? And bear in mind what we talked about in the previous video, which was the motor effect. So that was movement caused, being produced from alternating current in the presence of a magnetic field. So here we go. So we've got our AC supply, that could be from whatever music track or audio file you're listening to, okay, that will send a set of alternating current signals through our coil, okay, that is obviously going to be present in the magnetic field, okay, and depending on the direction of the current, so if it goes in one direction one way, it's going to cause the diaphragm or speaker cone to move in one direction. Then when the current goes in the opposite direction, the speaker cone is going to move in the opposite direction as well. Okay, so eventually we're going to get our speaker cone vibrating to the set frequency or set audio signal that the original audio track had. Okay, and we're obviously going to get some sound vibrations which do correspond to that soundtrack, that sound file. What would happen if the coil was connected to a DC supply? Well, it would literally just cause the cone to move in one direction. Okay, now let's look at the next useful thing that electromagnetic induction does or helps us out in everyday lives, and it's the transformer. Okay, and we're going to be looking at the transformer in the national grid, or which obviously is the system in the UK that allows electricity to be transferred to our households from power stations in our country. Okay, so what is a transformer? Okay, so they're not robots, first of all. So they're made up of an iron core, which is this section B here. Okay, it's shaped like this. And on either side of the iron core, we've got coils of wire. Okay, now, so we're going to go from left to right. So in section A, we call this the primary coil. Okay, it's on the left-hand side. Okay, and it's linked up to an AC supply. Now that AC supply is going to be coming from your alternator, which is going to be inside your turbine, sorry, inside your generator, inside your power station, okay? So just to recap, obviously we've got a fossil fuel, or it could be a nuclear fission power plant, but essentially we're going to get thermal energy being generated, okay, when we heat up those fossil fuels or when we break down that uranium fuel. That's going to heat up some water, and that water is going to turn into steam in a highly pressurized container, and then that pressure is then going to turn a turbine which will be connected to a generator, and that rotational movement, as we've said, okay, here, okay, is going to be moving a coil which will be in the presence of a magnetic field, which will then generate alternating current like this. Okay, so we've talked about that. Now, an alternating current, we know from our P12 lesson that from the right-hand screwdriver rule, that when we have got current passing through a wire, we've got an accompanying magnetic field going around it as well. Okay. Now, and obviously when it's arranged in a coil, that magnetic field comes in the form of like it's a bar magnetic field, okay? And what the iron core does, it essentially concentrates that magnetic field that is generated when we get current being passed one way through the coil, in the primary coil, and then in the opposite direction in the primary coil. So essentially we generate an alternating magnetic field in the transformer. Okay, so inside this iron core we're going to have a concentrated alternating magnetic field. That alternating magnetic field, okay, imagine this time the coil is staying stationary, but this time our magnetic field is changing, okay, and because it's changing it's going to induce an alternating current and voltage in the secondary coil. Okay, so there are two forms of transformers. One is the step-up transformer, which is the one you see here in this diagram here. That's when you have less coils in the primary core compared to the secondary core, which has got more coils. Okay, and the other type of transformer is of course the step-down transformer, which is when you have more coils on the left-hand side compared to less coils on the right-hand side. And what we're going to assume is that the power, which is the rate of energy transfer, which is energy divided by time, has to equal the power in the secondary core if we're assuming there's 100% efficiency of energy transfer from the primary core to the secondary core. Okay, let's remind ourselves of the power equation, okay, that we learnt in the electricity topic. It is voltage times current. Okay, so we're saying that the voltage in the primary coil times the current in the primary coil has to equal the voltage in the secondary coil times the current in the secondary coil. Okay, that's assuming it's got a efficiency of 100%. Now, in reality, obviously, it's not that it's not the case, but for the sake of calculations, we're going to say it's 100% efficient, and we can do this calculation here. Okay, so in your exam, you could be given any three of these values, and you would have to work out the fourth one. Okay, so just make sure you're comfortable with rearranging this equation. Now, why is a step-up transformer, why does voltage increase? Because that's what happens in a step-up transformer. Well, essentially, if you think about the length of the wire increasing, that means the current that was produced here is going to be higher compared to the current here, because there's less resistance, there's less length of wire for the electrons to pass through, which means we don't need a high voltage. Whereas in the secondary core, if we've got a longer length of wire, that means that's going to be greater resistance. That means we're going to need a higher voltage to pass current through that wire. So essentially, in a step-up transformer, we get voltage being increased, okay, because this equation suggests that these values have to either be the same, or one has to be greater and one has to be smaller in order to keep this product the same. Okay, so give you a quick example. Let's say it was 10 times 1. This has to either be 10 times 1 or 1 times 10. Okay, or some other product that ensures that it is still 10 watts. Okay, so but I've already told you that the voltage has to be increased because voltage pushes electrons around the circuit, and in this case we've got a greater resistance, so that's why we're going to get a larger voltage and a lower current. The other equation that you need to know with transformers is this one here. Okay, so it's a voltage in the primary core divided by voltage in the secondary core has to equal the number of coils in the primary core divided by the number of coils in the secondary core. Okay, so again, you could have the S's on the top and the P's on the bottom, as long as they're consistent. Okay, again, in your exam, you could be asked to work out one of these four values here, and they would give you the other three. Okay, so just make sure you're comfortable with rearranging this equation. So, where are step-up transformers used? Well, they're essentially used just after our power has been generated, or that rotational kinetic energy has been converted into electrical energy in our generators. And why do we step up transformers? Well, to increase the voltage, because as I said, that's going to reduce the current. And if we think about the long distances that the electricity has to travel from the power stations to our homes, it is a huge distance, which means we do not want energy to be wasted. And if we have a low current, it means we have less energy being wasted as heat in the wires, okay? Because that means the resistance is going to be low as well, okay? Because current, the electrons aren't going to crash into as many positive ions all the atoms inside the wire, which means we're going to get less friction and less wasted heat energy. Or a step-down transformer is used? Well, they're used close to our homes. Okay, so this essentially will reduce the voltage and increase the current, so that we're able to use them use our electrical devices which do not require 400,000 volts, which is what the step-up transformers increase the voltage to. Okay, so that's one reason why step-down transformers are used. Okay, and it's also for simple safety. Okay, at homes we do not need that high voltage. Okay, so just bear in mind this last point here. The advantages of power transmission in high voltage cables are less energy is lost as it travels down the cables, as it has a smaller heating effect. Okay, because when current flows through a resistor, it transfers energy as heat. That heat obviously goes into the surroundings, so we get a lot of energy being wasted if we have a high current. Okay, so please pause this video at any point, please rewind it, okay? I've also got some IGCSE physics videos that does explain a lot about transformers, electromagnetic induction, so please have a look at those videos where I actually draw some diagrams and go through some of these concepts step by step, and I do give you some numerical examples of using transformers and these equations as well, okay? But that is the end of P13.